your model isn't. Is it a Big Bang model with an initial emergence out of nothing and then eventually a collapse back to that?
No.
No. So,
No.
okay, so how do you conceptualize that?
Well, first of all, it is a Big Bang model. In other words, there is a Big Bang, but the Big Bang was not the beginning. The model, the reason people have trouble with this model, I think, is you're probably going to have trouble with it, and you're not unique in this. You see, people tend to think that if you have a model in which it keeps on going in some sense, and your Big Bang is not the beginning, that you've got to collapse back. So it expands and then it comes back, and then you're back with. But this
It seems
model
simpler that way.
Yes, but this model is not like that, and that's where you've got to get your mind around it.
Okay.
And people have trouble, and I agree with it. It is a crazy idea, and I admit it's a crazy idea. The trouble is, it seems it's quite likely it's true from certain observational things. But it's crazy too. It can be crazy and true at the same time.
Yeah. That's like a definition of life.
Yes, but you see, in this model, the universe expands and it expands, and this exponential expansion we seem to see, the stars seem to be starting to go away from us, these very distant stars that people look at, with an increasing speed.
Right.
It seems to be this exponential expansion.
Mm-hmm.
And
that's what's driven the dark energy hypothesis, I presume.
That's what they call it. But let's say that this is right. It's a cosmological constant. The universe expands and expands, exponential expansion. Now you might ask, who's in this universe eventually? Not us. The black holes will all have evaporated away by Hawking evaporation. They've swallowed galactic clusters. What's left in the universe? Pretty well photons. Now, giving the simplified version of the theory because there's some questions about it still. But let's say it's dominated by photons, which is pretty well true, but not. Let's take that.
Okay.
Now, the trouble with photons is that they don't feel the passage of time.
Right.
And more importantly, the equations governing light are the wonderful equations due to James Clerk Maxwell, the Maxwell equations. And the Maxwell equations have a very interesting property, that they can't tell big from small. They're what's called conformally invariant. That if you have a system in which you've got some electromagnetic field, and you could stretch this system to bigger or smaller, it doesn't notice the difference. The equations work just as well. And you can squash them here and stretch them here.
Well, and is that in part because space really doesn't mean anything to a photon?
In a sense. Well, it's the scale of space. You see, it's what we call, there's a term which I'll use here, it's called conformal. Conformal means big and small. I very much like, we talked about Escher a minute ago. There are these Escher pictures called circle limits, where he describes what's called hyperbolic geometry, but don't worry about that. The most famous one is these angels and devils. And you see there's a circular boundary. And they look as though they get smaller and smaller and smaller as they get to the edge.
Yes.
Now, as far as those angels and devils are concerned, the little ones are just the same as the big ones.
Right.
They don't know that they're smaller towards the edge. And that, to them, is an infinite universe. But to us, we can see, no, there's this infinity, which is just sitting there. And these angels and devils, if they don't know big from small, I'm not sure, I have a bit of trouble using this to explain things because the angels and devils do have a size in the picture. But you see, if they were made of massless material, that wouldn't know big from small. So if they were made of just electromagnetism, then big and small are equivalent. And so you wouldn't know when you got to the edge of this universe. So that infinity is just like anywhere else. That's the difficult concept in this thing, that the photons reach infinity without realizing anything funny has happened, if you put it like that. Infinity in this conformal picture is just like anywhere else. It's only mass that knows the difference. If you want to build a clock, you need mass. And this comes from the two most famous equations of 20th century physics. And the two most famous equations, one of them is Einstein's E equals mc squared, of course, which tells us that energy and mass are equivalent. And the earlier one was Max Planck's E equals h nu, or E equals hf, whatever you call the frequency, which tells you that energy and frequency are equivalent. Put the two together, that tells you mass and frequency are equivalent. So that means that if you have a mass, it is a clock. It has a frequency simply determined by its mass. And this fact is really the basis of modern clocks, which are extraordinarily precise. They don't directly give this because the frequency is much too high. You have to scale it down. But roughly it's the same idea. So a mass is a clock. But the other side of that coin is if you don't have any mass, you don't have any clocks.
So you don't have any time.
You don't have any time scale. You don't have any distance measure. So if the world is inhabited only by massless things, say photons, then it doesn't know big from small. It doesn't know hot from cold. And so the idea is, and this is where you have to take a deep breath, the idea is...
as opposed to all the other parts of this conversation.
Yes, the idea is that the remote future is indistinguishable from a Big Bang, so long as there is no mass around. Now, the remote future, the reason you have no mass around is basically, listen, there's a complicated part of the argument, but let's say it's because it's mainly photons. That's good enough. What about the other end? What about the Big Bang? Well, there's lots of mass there, surely. But the thing is that at the Big Bang, things get so hot, things are moving around so fast, if you like, that the energy, or the mass energy, mass-energy, the concept of mass, according to Einstein, is almost entirely in their motion. And that the mass becomes more and more irrelevant the closer you get to the Big Bang. So again, you have a situation where mass is effectively zero. And
so is it your claim, belief, theory that when things ground out in a universe that only consists of electromagnetic radiation, that is now a precondition for an event like the Big Bang?
In a sense, yes. I'm saying that the physics which is going on at the very remote future is extraordinarily like the physics going on at the very beginning.